Yesterday we gave you 3 details of the Rutherford model of the atom, also known, by the way, as the planetary model of the atom. I want to real quickly review those 3 details, and then I want to use that as a transition into another model of the atom, the Bohr model of the atom, that you've probably heard about in chemistry class as well. In essence, the gold foil experiment, also known as the alpha scattering experiment. I want to mention that name because oftentimes on our diploma exam, they don't call it the gold foil experiment, they call it the alpha scattering experiment. If you see that, it means exactly the same thing. Why do they call it that? Well, I'd rather call it the gold foil experiment, but I see why they call it that. Because in the end, what you're doing here is scattering alpha particles. Alpha particles going towards this really, really thin layer of gold foil, and then what do we find happens? Most of those alpha particles go straight through. Some of those alpha particles change direction. Some of those alpha particles are deflected. And then you get a few of those alpha particles that bounce back. Not very many, but a few of them that bounce back. And what do we find? What conclusions do we draw from those 3 different observations of what happens to these alpha particles as they go and strike this gold foil? Well, the fact that they go straight through, the fact that the vast majority of them go straight through, tells us that the vast majority of the atom, of gold atoms, must be empty space. Because if it's not empty space, then you're not going to have the alpha particles going straight through. Something's going to happen to them. If most of them go straight through, then it must be because they didn't encounter anything. It was mostly empty space. Now, a few of them deflected, which means if they deflected, they must have encountered something that pushed them away from the straight line path. They must have encountered something that was repulsive, that repelled them. If these are positively charged, the only thing that would repel them off of a straight line path would be something that was positively charged. Now that something has to be small because most of it's empty space. It has to be something small and something positive. We'll call it a nucleus. This is the discovery of the nucleus. Now a few of them bounce back, not very many, but the fact that some of them bounce back tells us that this small positive nucleus must be heavy, must be dense. And what does it tell us that? Well, because in the end, if you have a really, really light small positive nucleus, then when something moving, an alpha particle moving at a high speed hits it, it's going to knock it out of the way, and the alpha particle is going to go through again. The fact that the alpha particle bounces back means that it hits something solid, right? You got a water bottle. I got a water bottle sitting on my desk that's empty, and I throw an eraser at it, the eraser is going to knock the water bottle out of the way. If the water bottle is filled with water and the eraser hits it, the eraser bounces back, right? If it hits something that's light, it keeps going. If it hits something that's heavy, then it bounces back. The fact that a few of these bounce back tells us that the nucleus is heavy. So now we got our planetary model of the atom. Small, dense, positive nucleus, that's like the sun, with electrons orbiting around it. That's like the planets orbiting around the sun. All right? Dalton solid sphere, Thomson plum pudding model of the atom, and now we've got our Rutherford planetary model of the atom. Now we're going to zip forward to another model of the atom that we call the Bohr model of the atom. The Bohr model of the atom has some similarities with the Rutherford planetary model of the atom, but some differences as well. I'm going to point out 3 things that are going to distinguish it from the Rutherford planetary model of the atom. If I'm Niels Bohr, I come along and say, and examine Rutherford and his assistants' results and say, you know what, there's a lot of things I like about this. The fact that there's a small, dense, positive nucleus, yeah, I like that. That works for me, okay, if I'm Niels Bohr. The fact that the electrons are orbiting around that small, dense nucleus, yeah, I like that. The fact that the atom is mostly empty space, yeah, I like that. But it doesn't quite work. We need to be a little bit more detailed, according to Bohr, with our model of the atom. First of all, we're going to talk about, Bohr is going to talk about electrons orbiting around the nucleus, not just anywhere they want, but rather on very specific levels. Electrons have to orbit on specific levels, not just anywhere, as Rutherford said they could do. Okay, Rutherford nailed it in that they could orbit around the nucleus, but he didn't specify that they had to be here or here, just that they can orbit around wherever they want. It's kind of like if you're running a race in elementary school in grade 3 phys ed, and you happen to have a track, okay, what happens? The phys ed teacher is probably going to take you outside and just say, listen, run around the track wherever you want. Okay, if you're in high school or junior high and you're running track and you're running, say, 400 meters, you have to run in your lane, right? The Rutherford model of the atom would be the grade 3 phys ed teacher. The Bohr model of the atom would be the grade 11 phys ed teacher. In grade 3, you run around the track wherever you want. In grade 11, you got to run in your lane. Okay? Now, each of these electron levels are characterized by a specific energy. So the energy of the electrons on the first level they're all the same. The energy of the electrons on the second level are all the same, but the energy of the electrons on the first level and the second level are different. Each level is characterized by a specific energy. And by the way, if you've taken chemistry, you know that electrons like to fill in those inner levels first, right? It's like you go to a hockey game. If there's empty seats at a hockey game, where are they usually? Up top, right? We like to fill in the lower levels first. And if there's any vacancies, we like to leave the upper levels empty. All right? Now, the second aspect of the Bohr model of the atom that differentiated from the Rutherford planetary model of the atom is something that we call stationary states. Stationary states. What does that mean? Well, if you think back to Maxwell, I mean, that's been a while now, very beginning of our previous unit, way back in like early May, Maxwell's theory of electromagnetic radiation said accelerating charges generate EMR. Accelerating electric charges generate electromagnetic radiation. Well, here's the thing. These electrons, according to Rutherford and Bohr, they're orbiting around the nucleus. When they orbit around the nucleus, they're going in a circle. And when things go in a circle, they accelerate. Not because they speed up or slow down, but because the direction changes. We call it a centripetal acceleration. According to Maxwell, these electrons orbiting around the nucleus should emit EMR, but they don't. They don't emit EMR. So the orbiting electrons seem to be exempt from the classical laws of physics. They seem to be exempt from Maxwell's theory that accelerating charged particles generate EMR. These orbiting electrons that experience a centripetal acceleration don't emit EMR. If they did, watch what would happen. Okay, here's the keys as I swing them around my head right now are my orbiting electrons. If they emitted EMR as they orbited around the nucleus, they would lose energy, right? If they're emitting EMR, then they're giving off energy. Watch what happens as they give off energy. They lose energy. What happens to them? They spiral into the nucleus, right? That doesn't happen. If it did, then we wouldn't be here talking about this because atoms wouldn't exist as they do, matter wouldn't exist as they do, and we wouldn't exist. Orbiting electrons don't emit EMR. It's as if these electrons aren't accelerating. In fact, it's as if they're not moving. It's as if these electrons are stationary. They're not, but it's as if they're stationary because they don't obey those laws, those classical laws of electromagnetism. They don't emit EMR when they move around in a circle. Finally, the last aspect of the Bohr model that separates it from the Rutherford planetary model, go ahead. How can we prove that electrons are moving? Well, we can't prove anything. Okay, all we can do is say, since the early part of the first part of the 20th century, our theory has been that electrons are orbiting around the nucleus, and nothing in the last 100-ish years has disproven that. So if we have that's the way the scientific method works, right? Is if we have a theory that has some evidence to support it, and then never has anything to disprove it, then that's what we go with. And odds are, I mean, we've done so much experimentation in the last 100 years that, you know, we can be pretty confident that we're right. Although we can never be sure, right? We can never be positive because, again, the way the scientific method works is we don't prove anything. It's a working theory until it gets disproven. Third aspect of the Bohr model of the atom that separates it from Rutherford, the idea of electron transitions. Electrons can jump to higher levels. As electrons jump to a higher level, they absorb energy. Now, that energy that they absorb is usually in the form of EMR, but not always. They can get energy from other sources as well, but it's usually a photon. Usually what happens is you got this atom, an electron absorbs a photon of light, light shines upon it, the electron absorbs a photon, it takes that energy, and it jumps to a higher level as a result of the energy that it received from that photon. But it can happen from other things as well, from other sources of energy as well. Now, electrons not only jump to a higher level, become energized, they can fall to a lower level. And when they fall to a lower level, they emit energy. And that energy will always be in the form of electromagnetic radiation. Specifically, think back to our EMR unit again. Radio waves are produced by oscillating electric charge, X-rays by rapidly decelerating electrons, gamma rays by nuclear decay. Infrared, visible light, and ultraviolet were all produced by, remember what I said? Transitions of electrons in atoms. This is what we're talking about now. Electrons making transitions from high levels to low levels, giving off infrared, visible light, ultraviolet, or occasionally something with a higher frequency like an X-ray, but that would be very rare. Okay? It's almost always one of those three. So the basic structure of the Bohr model looks a lot like the Rutherford model, but we get a little bit more specific. We start talking about electron levels. A, that there are electron levels. B, that we can make transitions from one level to another. And C, that these electrons, as they orbit around on levels, it's as if they're not moving, but they are. Yep. No, I mean, by saying a lower, that's a good question. By a lower level, I mean closer to the nucleus. Okay, so level 1 would be the level that's closest to the nucleus. Level 5 would be further away from the nucleus. When we jump to a higher level, we're going from level 1 to level 5. We're going further out. Okay, it's like we're climbing a ladder. You know, fall to a lower level, we're going closer to the nucleus. Okay. I know when you're on track, I know that when you're in lanes, you know, say you're in the 8th lane. Okay, obviously, the distance around the first lane is 400 meters. The distance around the 8th lane, I'm not even sure what that is. So you have a staggered start, right? Because to make it fair, right? So you're all running the same distance. But let's say for a second that you didn't. Let's say that you all start in the same place. Okay, you're running 400. You're running once around the track. The person inside on the inner level, on the inner lane, has to run once around. You on the outer lane has to run once around, right? Okay, you're on an upper level. What do you want to do? Well, if you've got to run once around the track and everybody's got to run once around the track, then what do you want to do is, if there happens to be a vacancy in the third lane, that's the lane you want. Or if there happens to be a vacancy in the first lane, that's the lane you want, right? So the inner levels or the lower levels, first level, second level, third level, are the desirable ones. That's the one where everybody wants to go to. The outer levels or the higher levels, that would be the 7th lane, the 8th lane, further away from the nucleus, further away from the field, the infield. All right, flip your page. Take a look at this diagram. The reason that I photocopied these notes for you in color was so that you could see exactly what we see right here. 3 diagrams. 3 diagrams here. I want to separate them into kind of 2 groups. There's the first picture, and then there's the second picture and the third picture that kind of go together here. The first picture it doesn't really have anything to do with electron transitions, but it's going to be used as a reference diagram. The second picture and the third picture involve electron transitions. They involve either this or this. And again, the first diagram is just as a reference. Let me explain that first diagram first, though, that reference diagram, so that we have something to compare the second and the third diagram to. Let's say we've got a light bulb, okay, a heated solid, an incandescent light bulb, like a regular old style light bulb that you don't actually see all that often anymore. Maybe it's a liquid, maybe it's a gas under high pressure, but it's heated. It's a heated solid, it's a heated liquid, or it's a heated gas under high pressure. It emits light. In fact, it emits all colors of light. It emits what we call a continuous spectrum, all colors of the rainbow. But it comes off as white light. If you have one of the old style light bulbs at home and you flip on the light, you don't see a rainbow, you see white light, whitish, yellowish light coming from it. But if I put that white light through a prism or a diffraction grating, then it separates the light, right? Prisms separate the light by dispersion. Diffraction gratings separate the light by diffraction. If I had a prism, then it would get, think back to your last unit test. If I had a prism, then I would get a single continuous spectrum produced: red, orange, yellow, green, blue, indigo, and violet. If I had a diffraction grating, then I would get multiple spectra, multiple continuous spectra. A spectrum here for the first order max, another spectrum here for the second order max, and so on. And it would be reverse order. Instead of red, orange, yellow, green, blue, indigo, and violet, it would be blue or violet, Vibja, Yor, right? Opposite to Roy G. Biv. Otherwise, same effect, right? It splits it up into continuous spectrum. White light, okay, which comes from a hot solid or a liquid or gas under high pressure, produces a continuous spectrum. Whether it's by a prism or diffraction grating just depends upon, the exact result we get depends upon whether you use a prism or diffraction grating. In other words, how many of them we get and whether it's Roy G. Biv or Vibja Yor, okay? All right, there's our reference. Nothing to do with electron transitions. Now, let's take hot gas and put it under low pressure now. So we had a solid or a liquid or a gas under high pressure. Now let's take a gas and put it under low pressure. It's hot still. Produces light. And when we look at it, it might appear to be white, okay, white light. But we put that white light through a prism or a diffraction grating and we see all of a sudden, wait a second, it wasn't all the colors of the rainbow. And we know that it wasn't all the colors of the rainbow because when we look at a screen that's detecting this light, this is what we see. It's called an emission spectrum. Sometimes I'll call the line emission spectrum. We see a single band of light right here, and then another one right here, and then a couple more right here, and then another one right here, and then a couple more right here. Instead of getting all the colors of the rainbow, I get very specific lines corresponding, listen carefully, corresponding to individual photons that are emitted because of specific transitions. So this red line here happened because an electron made a transition from the third level to the first level, or whatever the case may be, and emitted a specific photon. Okay, this blue one over here happened as a result of a specific transition in a specific element releasing or emitting a specific photon. So this is what we call a line spectrum or an emission spectrum, a spectrum that's showing us photons coming from specific transitions, as opposed to the continuous spectrum, which is showing us all the colors of the rainbow because that's what we had, right? Hot gas under high pressure, solid liquid, produces all the colors of the rainbow. Under low pressure, the light comes from transitions of electrons, which gives us specific photons. Was there a hand up, Carrie? Was it you? That's why elements have pigment. What do you mean exactly? You mean like produced color? Like what's the term chemistry they use? I think in chemistry he shows like a spectroscopy thing where it shows colors that come from specific gases. Sorry? No, no, no. They'll show you. I think in chemistry they'll show you light that's produced from certain elements. Yeah, that's like the spectroscopy, and yeah, that's where that comes from. Now, let's take a look at the next diagram, and then I want to tell you a couple applications of this here, okay, where we might see it beyond a classroom type thing. What do we have in the third diagram? Well, this time we have a light bulb, or maybe we've got a liquid, or maybe we've got a heated gas under high pressure again. So basically, we've got diagram number one. In fact, we've got exactly diagram number one, except we've got a cold gas in there, cold gas in between. Let's take that cold gas out for a second. Gone. Now all we've got is exactly diagram number one. And diagram number one has a continuous spectrum. So we've got a hot solid, hot liquid, or hot gas under high pressure. We get a continuous spectrum, all the colors of the rainbow. But if we put a cold gas in there, think logically about this. Don't try to remember it. Logically think about it. If we put a cold gas in there, what's going to happen? There's heat. Another example here, an analogy. There's heat. You're cold. What happens? You absorb heat, right? When you're cold, you absorb. This cold gas absorbs photons. And those photons cause electrons to jump to higher levels. What do we see on the screen? Well, in the absence of the cold gas, we'd see a continuous spectrum, because that's what we see with a hot gas under high pressure, or a solid, hot solid or hot liquid. But if we've taken away specific photons corresponding to specific transitions, then we're going to have the continuous spectrum minus a few photons. So we've got a continuous spectrum, except for this, and except for this, and except for this, and this, and this, and this, and this. These correspond to transitions from high to low levels where photons were given off. The diagram on the bottom corresponds to photons absorbed, causing electrons to jump to higher levels. What do you notice about the second diagram and the third diagram, though? I mean, besides the fact that they're kind of, one's got a lot of bright light and one's pretty much dark. Dark? The lines are in the exact same spot. That tells us that the element or the gas that produced this emission spectrum is exactly the same composition as the gas that produced this absorption spectrum. Now, the gas here was hot, the gas here was cold, but it's the same composition. All right? Each element, each gas would have its own unique spectrum, which leads us to some applications of this, right? I remember when I went to my first year of university, never did any of this stuff in high school, never knew. Your age, right now, you know more about this than I knew when I was your age. I went to university and one of my professors, this is what he did. Like in university, science professors, they teach a couple classes and then they do research. That's their job, really, is research, right? This guy's research was spectroscopy. He would analyze different gases and essentially photograph them. Photograph the spectra, the line spectra, emission or absorption spectra of different elements. And I remember when I first saw his lab and first saw what he did, I remember thinking, yeah, that might be nice for the first couple that you do. Like, hey, look at this pretty picture that I got. But after a while, it's like, oh my goodness. Like, what could you possibly use this for in the world? And then I learned, as I got to know this guy, he's an astronomer. He's an amateur astronomer. That wasn't his job. He just liked astronomy. And that's why he did this, is because he liked astronomy so much. When you look up at a star, let's say you look up at the sky tonight and you discover a star. And it happens. Every once in a while, an amateur discovers something that nobody else has ever discovered. You're looking up at it and you're like, oh, there's a brand new one. Nobody's ever observed that before. I wonder what it's made of. So you look at the light that comes from the star through a spectroscope, which is basically a prism or a diffraction grating. And that spectroscope splits up the light. And you observe this spectrum, this exact spectrum. What do you know about the composition of that star? You know that it's made up of whatever element caused that spectrum, right? You've just determined the composition of that unknown gas that made up that star just by looking at the spectrum that's produced. Yep.
So when the light goes through the cold gas, it absorbs the photons?
Yes. Yeah, electrons within the cold gas absorb the photons and cause the electrons to jump up. Yeah. Does that kind of make sense? Yep. Yeah, it is. You know, that's exactly what it is. That's a good analogy, actually. That's a really good analogy. It's like a fingerprint for each element and in each mixture of gases. Yeah, because in the end, everybody has a different fingerprint, right? Well, every gas, every element has a different unique spectrum that's produced, a different emission spectrum that you would see, and corresponding absorption spectrum. Let's have a look at 3 spectra here. They're black and white. You know these would be different color, right? But in the end, it doesn't really matter because we can see where the lines are. These are emission spectra. Pretend they're different colors. We have high wavelength over here. On the right-hand side, that would mean it's a low frequency. And of course, since it's a low frequency, high wavelength, it's going to be a low energy. That means that this photon right here has a higher wavelength, a lower frequency, and a lower energy than any of these lines over here. 3 different unique lines for a hydrogen gas spectrum. How do we know it? Well, because somebody took pictures of it, right? Somebody did an experiment to observe the spectrum for hydrogen, and it took pictures of it so that we would have something to compare gases to. Helium, same deal, although you can clearly see that it looks different than hydrogen, as it should, just like Carrie's fingerprints look different than Nick's fingerprints. And then sodium, which has a completely different spectrum, but again, a couple lines, real close together though. This one has a slightly lower wavelength and a slightly higher frequency, slightly higher energy than the second one then. 3 different reference spectra. Now what we want to do is compare this one, the unknown gas spectrum, to the 3 known gas spectrum. So let's look at them. You guys have got these on your sheet. I want you guys to tell me what element or elements make up this unknown gas mixture. I just observed this through my spectroscope when I'm looking at a star that's never been observed before. Nobody's ever seen before. Okay, what makes up that star? What's present in that star? All right, what is it? Is hydrogen present in an unknown gas mixture? We know that hydrogen is in fact present, not because all of the lines in the unknown gas are present in hydrogen. They're not. But rather because all of the lines in hydrogen are present in the unknown gas. So these 2 are hydrogen. This one is hydrogen. This one is hydrogen. Hydrogen must be present in an unknown gas. But what do we know about that unknown gas? Not only that hydrogen is present, but that something else must be present as well. What else is present in it? Sodium, because we've got these 2 lines corresponding to the 2 lines in sodium. So this unknown gas mixture would be made up of hydrogen and sodium. Make sense?